Good morning. And I have a question for you. Is this bike wheel moving? Does it have kinetic energy? Right? So that's the question. Normally we say, yeah, it's moving. The thing's spinning. You can obviously see these things going, right? But kinetic energy is 1/2 mass times speed squared. This thing, in order to have speed, remember it needs to move a distance, right? So if we think about a wheel, most of the time, if you are doing something with a wheel, it's going to actually like roll on the ground. And if we break that down just a little bit more, right? If something is moving a distance or displacing on the ground, its center of mass is moving, right? So you can tell this thing is actually moving right now because its center of mass is moving linearly. But right now, obviously this thing is moving. We can see it moving, but its center of mass is not displacing at all, right? So we need a different way to describe moving, right? So this is rotating. So it has movement, it has rotational movement. It does not have translational movement, right? So yeah, then the question of kinetic energy, does this have kinetic energy? Well, kinetic energy has to do with movement. We know that this is moving rotationally, right? So we can describe this better by saying, yeah, right now, this has rotational kinetic energy. And then when it's not rotating, and then its center of mass is moving translationally, we could say this has translational kinetic energy. That's the normal kinetic energy we've been dealing with. But what if this is doing a standard wheel thing and the center of mass is moving and the wheel is rotating, right? So if it's spinning and this wheel is rotating, we're going to say that has both types of kinetic energy. This now has rotational kinetic energy, as well as this has translational kinetic energy. Because it's moving, it's translating, it's moving linearly, okay? So yeah, is this moving? The answer is yes, but we got to be a little bit more specific because this is rotational movement. So it has rotational kinetic energy. So the question of what does this mean comes into play. And what does this mean when we're dealing with energy stuff? Well, what this means is, if something is rolling, that the old adage is without slipping, meaning that when an object is, let's say, a baseball, okay? If a baseball is rolling across the ground, that tells us that its center, give me that red one, that center of mass is moving to the right with some velocity. So that's the velocity of the center of mass. And then also this thing would be rotating with some angular velocity, right? Omega, that's the term, the symbol for angular velocity. So this would have kinetic translational motion represented with K, usually TRA or tran, right? And then it would also have kinetic, and we call it rotational energy. So this would have both those types of kinetic energy. When we talk about conservation of energy, actually we don't even get to that yet. Let's talk about the formulas for this. So you have done plenty of conservation of energy problems where you've dealt with translational kinetic energy. Okay, that is the formula for translational kinetic energy. We have 1/2 mass of the thing that's moving times the speed of that center of mass squared, or velocity squared. Doesn't matter because it's getting squared, right? Now this is where we have a little bit new of a formula, but similar, right? So it's still 1/2. Remember, when we talk about rotation, mass is not necessarily as important anymore. It's how that mass is distributed, and we call that rotational inertia. And we represent it with a capital I. And if you don't know what that is, I would watch some of the previous videos. And then instead of just straight linear speed, v, we have angular velocity, omega, and that's squared. So really similar, right? Instead of mass, we have rotational mass, rotational inertia. Instead of linear speed, v, we have angular speed, omega, right? And other than that, the formulas are the exact same. But if we're talking about just kind of conceptually, if we're talking about conservation of energy, let me set up a problem here. So in this problem, we have a block that is up on some ramp, and let's say that this ramp is a height y above the ground, okay? So we have this block that is a height y above 0. The block then slides down the ramp, and at the bottom of the ramp, it has some type of speed, right? So if we think about conservation of energy, or the LOL diagrams we used to draw to represent conservation of energy, we would have this type of setup where I have my initial little chart. In my system, I have the block, and I'm going to have gravitational potential energy, so I need the Earth in my system as well. And then that's it. And this is a frictionless ramp, so we don't need to worry about like friction taking energy out or anything. And so when I look at conservation of energy, think about what are the energy bars that could show up. At the beginning, I have all gravitational potential energy. Let's give it 5 blocks. 1, 2, 3, 4, 5. So that's all initial gravitational potential energy. Over at the bottom, all of this energy has been put into making this thing slide. It's just a block. It's not rotating. It's not doing anything like that. So at the end, it's also going to still have 5 blocks, 1, 2, 3, 4, 5, of kinetic that's now moving linearly. So we could say translational kinetic energy. And the energies that we have, we say all of this initial gravitational energy has to equal all of the translational kinetic energy at the end, right? That's nothing new. That's what we've done before. But let's say we have instead of a block, let's put something that's going to roll, like a ball. Okay, so here is our setup. Initially, we have this block of mass m, and it is, let's say that just like before, this is a height y above the ground. All right, and if we look at our LOL diagrams, it's going to be really similar. Right, we have the ball that starts up here in the system, and then the Earth is going to be supplying the gravitational potential energy. And yeah, so let's take a look at what we have. At the beginning, it is, let's say that it's not moving, right? And at the end, it has a linear or a translational speed. So yeah, the center of mass is moving at the end. But also take a look at now, we now have this rotational velocity as well, this angular velocity. So let's start just like we did before. At the beginning, it's not moving. There's 5 blocks of energy. Right? And that's all in its initial gravitational potential energy. Now, here's the big difference. At the end, this thing is moving translationally as well as rotationally. So maybe now there's 4 blocks in translational kinetic energy and 1 block in rotational kinetic energy. So if you take a look at what that means is now I have all of this initial gravitational potential energy, and that's now equal to the sum of these different kinetic energies. Why this is important is this means that if something is rotating, remember all of this energy before got put into making it move linearly, right? This would be going, the original one, where it's only kinetic energy translationally, that would be moving faster because it has more energy to put into that linear moving account, right? If I'm talking about spreading out the energy between these two, well, now there's not going to be as much energy to put into this translational kinetic account, right? Some of the original energy has to go into rotational. So if something is rotating, it's not going to be moving as fast at the bottom because some of its energy got used up to make it rotate. Okay, so let's take a look at some problems. And I didn't actually cut and paste these yet, so let's just take a look at them. Right? Yep. Two hoops with the same mass and radius are released from rest at the top of two identical ramps. One hoop rolls without slipping, one slides down the ramp. So we got two hoops, one rolls without slipping, one slides. So if it slides, that means it's not rolling. Okay? So the question is, which reaches the ground first? And I know the one that is not rolling is going to have more energy put into its linear speed. In other words, it's going to be going faster, so it's going to reach the ground first. So the object that is sliding will always reach the ground first. Let's see. Huzzah! I was getting them all wrong so I could get some... Maybe I did put... Let's see. Oh, I did. Right? So that's pretty much a hoop and a block of ice with the same mass are released from rest. The hoop rolls without slipping, and the block of ice just slides down. So the question is, which reaches the ground first? And that's just like the example we did earlier, the sliding one, right? The one that's not rotating. All of its energy is going to be put into moving fast. So it's going to be going faster at the bottom, so it's going to reach the ground first. Okay. A hoop and a disc with the same mass are released from rest. The hoop rolls without slipping. The disc slides. Doesn't matter. Same thing, right? The one that's sliding is going to be moving faster, so it will get to the ground first. All right? And that's pretty much it, ladies and gentlemen, for kinetic energy. You just need to know that energy gets split up between those translational kinetic energy account and the rotational kinetic energy account. That is all you need to know. All right. Have a good day. I will see you later.